All right, well, hello everyone. I'm Vanessa. I'm currently a grad student at the University at Albany. I'm working with Dr. Kara Sulia, who is the PI on this project. And I also want to acknowledge collaborators Zach Lebo at the University of Wyoming and Carl Schmidt at the University of Alaska Fairbanks. So as was already introduced, today I'm talking about the classification of cloud particle imagery and thermodynamics, which we've given the acronym of COCPIT. That's primarily because this work focuses on the Cloud Particle Imager probe, the CPI probe, which is an optical array probe that flies underneath the wing of an aircraft and flies to the cloud and captures images. You can see some examples here that surround the picture in the upper right-hand corner. It's a fairly high resolution probe compared to other probes that are available at 2.3 micrometers, and it can see ice particle ranges up to about 2.5 millimeters in size. Not only does it capture images of frozen hydrometeors, but also cloud droplets and liquid water, as seen in the example imagery here. And then on the bottom right, you can see a table that has 8 different past field campaigns and the associated number of images in the rightmost column. And these numbers here are summed across multiple different flight legs per campaign. And then if you sum all 8 up, it comes out to be over 8 million images that are available in archives. However, there's really no great consolidation of this data, or at least no fantastic documentation given such a massive data set. And so we feel that it's fairly underutilized at the current state. And so because of this, we would like to archive not only the particles and their properties that are coming out of these images, but also be able to co-locate them with other environmental properties from different probes that might also be flying on board. And this would just be done through time matching. And so in doing so, we could potentially eliminate any time-consuming pre-processing phases for other research scientists, solely because they would have to focus on how to not only download and extract all of this data, but then figure out how to separate all of the data into the specific particle types that they would be interested in looking at for their scientific objectives. And so our end goal here would be to create an automated and a very user-friendly data product, specifically in the form of a database, something as kind of what's seen to the right here. And this database would have great filtering capabilities to it. So something filtering based off of not only the campaign or geographical location, but perhaps a specific particle type or environmental growth regime or temperature. I should also point out that there is a caveat to this work. We can't necessarily assume that where these ice particles are originating their growth from is going to be at the same geographical location as where the aircraft is flying through and taking snapshots of these images. They're likely going to have a convoluted trajectory toward the probe itself. And so because of this, we would like to estimate the detailed thermodynamic conditions that follow the both temporal and spatial history of these observed crystals. And this would be done by running backward trajectory models, specifically using the high slip model. Second here. So there's 3 main models to this work. The first 2 focus on pre-processing, which is definitely the timeliest portion. I'll first talk about the spheres model, which is a binary logistic regression model. You can see an example in the upper row here of images that would exhibit a cloud droplet representation, and then on the right side would be any other type of image that is either a hydrometeor in the frozen state or just a lower quality image. And so what our aim is to do here is to separate out all liquid and keep all ice particles. Before we could feed in all of the over 8 million images, we had to create a training data set, which consisted of 900 spherical looking droplets and then over 2,000 bad images. In this case, that would just mean any ice particles. And so once we had that, we could then sort of neglect the spherical liquid and keep all of these ice particles. However, there was still some less than ideal quality images within that data set. So we then had to further go ahead and create another preprocessing model, which we're calling the SIFT model, or Separate Ice for Training model. And what this does is it's sifting through the remainder ice images and separating out high quality images from low quality images, as seen on the bottom row here on the left and the right sides. And again, this is a binary logistic regression model. It's using the same predictors as the spheres model. However, there's somewhat of a different objective here. So we had to create a different training data set, which consisted this time of 1,000 in this case, good ice particles, which refers to particles that are fully in the frame, and examples of images that research scientists would be able to use. And then the bad side here was over 2,000 images of either blurry images or fragmented or shattered images from the inlet, the probe inlet itself, or images that weren't fully in the frame, meaning that there was a given percentage of the image that was cut off, or the pixels were intersecting the border or perimeter of the image too much. So after we had this final data set that's kind of in the red boxed area of these high quality images, we could then move on to the machine learning portion of the project, which is to then train a convolutional neural network for the different particle types, and this was based on classes that were predefined. So this is a conceptual process of the overview of the hand-labeled and training data sets that needed to be created. So that included the spheres model, the SIFT model, and the convolutional neural network. And then we could go ahead and start extracting out all of our raw data from the CPI probe itself. So this would be in the yellow bars up at the top where it says process sheets. And by sheets, I just mean that the way that the raw data is coming out of the probe are multiple images per frame, or what we're calling per sheet. And so we had to go ahead and extract each individual image off of these sheets to be individualized by themselves. However, at this point, they were not all of the same dimensions. They were all different sizes. So we had to resize them so that the length and the width were equal to be able to be fed into the convolutional neural network. And then after we resized all of them and went through the pre-processing phases of the spheres and the SIFT model that was mentioned before, what was returned was a database of high quality images of ice particles. However, we noticed that there were some duplicates, specifically within the 2000 ARM IOP campaign. So we went ahead and removed those, and then we could ultimately feed the high quality images that didn't have any duplicates at this point through the convolutional neural network and append on specific probabilities of classification for each particle class. So here's just some statistics or overall results for both the spheres and the SIFT model. And this is with respect to each campaign in each row. On the first column is the number or percent of the liquid cloud droplets. You'll see totaling about 35% of the entire database of 8.6 million images was cloud droplets. And then moving on to the next column is the number or percent of quality ice particles. So that is the results from the SIFT model. And there's only about 9.1% of the entire database that does include spheres as well. So this number's fairly low, considering that there's only 787,000 total that are then coming out. And it is variable based on the criteria that we impose. Those parameters such as the amount of cutoff that we allow for these images, that number might vary by a couple % increase. And then the final column here would be the time to process each one of these campaigns, and this is in units of hours. So certainly a lengthy pre-processing phase, and I should mention that this was done in parallel on 80 different CPUs. So now moving on to the machine learning portion of this work, specifically the convolutional neural network, we turned to the PyTorch libraries and used transfer learning, specifically from the Torch Vision models, and I'll pull up, here's all the 8 models that we trained on, and these are nice because they have predefined architectures that we could use. However, they are trained on the 1000 class ImageNet dataset. So for our methods, we needed to retrain all of the model parameters and update each one of them because our images were obviously much different than what they were trained on. And I should also note that all of these models were hyperparameterized such that we found the ideal parameters to give the highest accuracies based on the batch size that we gave it, or learning rate, and dropout for overfitting, or the number of epochs we ran, and all of these good things. And then there's the histogram on the bottom here. This represents the training data set and the number of images per class, or per particle type that we predefined. So you can see all 12 here, and it does include some rhyming, some different rhymed particles in addition to pristine particles. And the order of magnitude would be in the thousands of images for this training data set. So now jumping kind of right into results. On the left, you're looking at accuracy of all of the different models denoted in different colors. And on the right is all the loss magnitudes for each of those models. The dots represent the training data set, which was 80% of those thousands of images. And then the stars represent the validation data set, which was 20% of the data set, held back so that the model didn't necessarily see the predefined labels. And so I'll kind of focus your attention on how high these accuracies are getting, specifically for some models well into the upper 90s. The model that did the best was the VGG19 model, which is the dark red dots. And this was above 99% accurate, not only on the training data set, but also on the validation data set by the 50th epoch. So we ultimately chose to save that data, that model rather, and then run all of this new data through that model. And some more results would be a confusion matrix that is displayed here. It is normalized based on the unbalanced classes that we had. And this was on data that the model had never seen before, but that we did hand label ahead of time. On the x-axis is what the model predicted, and on the y-axis was the actual labels that a human was distinguishing. And so what you want to see here are high probability densities along the diagonal or the one-to-one line. Again, this is just for the VGG19 model, but it's doing clearly a fantastic job at these predictions. To sort of wrap up here, in future perspectives, I have a plot that represents one potential project that could come out of this data product proposal. So the relative humidity from a specific probe is on the y-axis on the left side, and we have temperature on the y-axis on the right side. And so we're plotting a few different variables here, and this is along one flight leg with time increasing to the right. And then what I've done is overlaid different CPI images, kind of where they belong in the phase space. And so you'll see that as you increase your relative humidity or saturation within the cloud, you get these more complex or intricate particles in terms of how many branches are grown. And then you can see specific growth regimes as well. So this is just one example of the work that could be done from the database that's going to be created. And then here is just a conclusion slide and kind of an overall look at this project. So here's our final aim with the database on the bottom here. And the way that this would work would be one particle or image per row, and then it would have the date and the latitude, longitude, altitude all appended in separate columns. And then we would also have the machine learning portion where the convolutional neural network would then be, sorry, let me just check this time here. 1 second. So then the convolutional neural network portion would be appended into each column with a given probability for each particle type. And then you can see the thermodynamic mapping as well in the yellow rectangle here. And so that would be indicative of the columns that say temperature and relative humidity. And then the last thing would be that any high split trajectory runs, the backward trajectories would be appended where applicable for each one of these images. And with that, I think I will wrap up and see how much time I have here. Lost the time screen, but stop sharing. All right.
We have about a minute, so.
Sorry, I lost track of the timer there.
Yeah, about a minute left. So I just, if there are any questions, I see one comments from Scott Collins. And then maybe you could reply in the chat. And then from Joe, for transfer learning, did you just try retraining the end layers first before reordering all weights?
Yeah, I absolutely did, but there was an increase in accuracy by at least a few %, and so it was worthwhile to take the time to train all of the layers and redo all of that first. Yeah.
Thank you. I have one more question. The VGG19 has many hyperparameters, and it seems that your ice particle samples were more or less limited. So did you see any issues with that kind of data set?
What do you mean by limited? The number of classes that were limited?
Yeah, or the number of samples per class.
Yeah, so we do have a semi-automated approach for the hand labeling of all of these images, but it was mostly just myself hand labeling them. So certainly more data would help all of the hyperparameters within the VGG network. They were fine-tuned to the maximum capabilities based on the amount of images that we had trained on. that could obviously always be improved, and we could add more classes or take away classes to kind of group different particle types together a little bit better.
Okay, thank you so much.
You're welcome.
With that, thank you so much for your talk, and we'll move on to the next speaker.